All right, so I want to thank the organizers. I really did nothing this time. So our friends here at Stanford, and as well as Hugo and Masamichi, who I think were involved, and of course Liz, who's kindly recording all of this. So I'm going to talk about some ongoing work with Arvind Shabazzi-Moghadam, my former student who is now here, though I don't, is he here? There's Arvind. Okay. So part of this work has already appeared, and the rest hopefully will appear in the next couple of weeks. Maybe that's overly optimistic. Let's say a month. Okay, so we're gonna start with some review of really old GR stuff. Singularities are, I don't know, for me that was why I went into this field. I wanted to know how the universe started, what happens when you jump into a black hole, that kind of stuff. And to my disappointment, we have learned very little about them. And so I'm going to start by going back and reviewing how relativists even. Oh, by the way, am I supposed to take this off when I talk?
As you prefer.
Okay, let's take it off. It feels very. Okay. Yeah. So you have to first of all define what you mean by them, right? And in GR, what we usually mean by them is that the space-time has an incomplete time-like or null geodesic, meaning that after a finite proper time or a finite affine parameter, you can't extend this geodesic further, even though the space-time itself is inextendable. In other words, the space-time is not something you stupidly just stopped here, which would be a proper subset of a bigger space-time. It's as big as you can sort of make it. It's not the proper subset of any larger space-time. And if such a thing is present, you say that's a singularity. That is not a perfect definition for all purposes necessarily, but it's the thing you prove with singularity theorems, and it's pretty good. So this would be an example of a Big Bang singularity. This would be a singularity inside a black hole. And right, so maybe it's useful to have a new perspective on these singularities. So let's start with an old one. So this is the Penrose singularity theorem, for which he got the Nobel Prize a couple years ago. And it's very old, as you can see. It kind of started the new way of looking at GR that I think we all have grown up with. And it goes as, so why was there a need for a theorem? You can just write down a solution like this. Maybe it was clearer on the previous transparency. So this is, yeah, it's not projecting very well. This green stuff here is supposed to be a star that's collapsing. And you can find exact solutions where you model this as a ball of dust. So the dust ball looks like a portion of some cosmology, of some cosmological solution. And then you glue it to an exterior, which by Birkhoff's theorem just has to be part of a Schwarzschild vacuum solution. And since this is dust, it doesn't want to move in or out. It has no pressure. So this actually works at all times. And now you have your exact solution. This was found by Oppenheimer and Snyder in the 30s. But you might worry that the singularity is an artifact of the spherical symmetry that is present in this solution. Now, it's sort of like if you shoot particles towards each other and they all meet at a mathematical point, then that would look like it has some kind of divergence or infinite density. But in reality, everything is smeared out, and maybe they go around each other. And so as soon as you relax this, perturb this even a little bit, maybe there's no singularity. So what this theorem does is it lets you go back some ways from the singularity where the solution is under good perturbative control. And it lets you establish a criterion that's easy to check and which is going to hold in some open set of initial conditions. And conclude when that criterion is satisfied, or those criteria are satisfied, the assumptions are satisfied, conclude that there must be a singularity in the sense of this definition I gave, some incomplete geodesic. And so what are these assumptions? So what you need is a Cauchy surface, and so some sort of moment of time, and then a two-dimensional surface that splits that into two parts. That surface is always going to be called T here. And for Penrose, it was important that one side of this Cauchy surface is non-compact. Okay. So we need all of that. And we need, moreover, so I'm going to call that the exterior. It's just a name. Could be that both sides are non-compact. That's fine too. But we need at least one to be non-compact. And then what we need to be true is that the light rays that are coming orthogonally off of this Cauchy splitting surface T are contracting. In other words, as you follow them, they sort of transport an area along these orthogonal light rays, and the area is getting smaller. So that's a sign of some sort of strong gravity regime, right? You've got a sphere here, and you're sending light rays technically out towards the side that you would call infinity, or the outside, and yet the sphere is shrinking along those light rays because space is just collapsing so rapidly here inside the black hole. So that's called a trapped surface. It has to be compact, outer trapped to be precise. So outer refers to the fact that these light rays are going in a non-compact direction. It has to be compact, and the light rays have to be contracting. The quantity that captures this is called the expansion. Okay, so that has to be negative. In addition, we're going to assume the null energy condition, that the stress tensor contracted with a null vector is not negative. And we could sort of assume global hyperbolicity, though it's not actually essential. If you don't assume it, then you just don't know whether perhaps the incomplete geodesic that's predicted by the theorem might just be incomplete because it hits a Cauchy horizon. So this depends on whether you want to be sure that it's really a singularity. Okay. I think I mentioned all of the assumptions. So under those assumptions, you can predict that at least one of these orthogonal null geodesics coming out this way is incomplete. So that was the statement that Penrose proved. And I'm going to actually review the proof because the singularity theorem that Arvin and I proved you just switch out a couple of minor steps in this proof. And so once we do this one, we can piggyback on it, and we're done. And it's kind of a cool proof, so it's nice going over it. What we're going to do is kind of play two objects against each other. The first is this regular L. There's a dot up here. It's the boundary of the future of the interior of T. Okay, so going back to the previous slide, the interior of T is this region. The future is that region here. The boundary is precisely those light rays that we're worried about. Okay, that's the boundary of the future of the interior. Okay, here's another example. An example where there is no singularity because this surface here is not outer trapped. But if this is just Minkowski space, then take a sphere, look at the boundary of the future. It's this sort of truncated light cone that's coming out of that sphere. It's the yellow object here. That is this L. Okay. That's our object number one. Okay. Our object number two is going to be called curly L. And to define it, let's first, just for convenience, rescale the affine parameter of those light rays coming out of T so that it's everywhere -1. We can do that because T is compact. So we know that the expansion doesn't approach 0 arbitrarily closely if we know that it's everywhere negative. We don't have to do this, but it's convenient because then I can just say, let me consider all the points that are reached by the light rays until affine parameter 2. Okay, it'll be clear why I want 2, but right now I'm just picking that. I am now using, for contradiction, the assumption that there is no singularity. I'm assuming that all of these null geodesics are in fact complete. If I don't assume that, I don't know that I'm going to be able to get to 2. But by assuming that, I know I can follow them as far as I like. Okay, so in this Minkowski example, this would be a subset, right? L, the yellow L, regular L, the light rays just keep on going. And here I'm just picking the part that goes until affine parameter 2. That's the curly L. Okay. Moreover, because I know that T is compact, and this interval 0 to 2 is compact, I know that curly L is compact. It's going to be important. All right. So here, in this example, of course, there's no singularity because a key assumption of our theorem isn't satisfied. Now let's look at what happens if it is satisfied. So the expansion is everywhere negative. Then the null energy condition implies that all those light rays must intersect each other, either locally or non-locally, and leave the boundary of the future. In other words, they must exit from the regular L. To be able to draw this, I have to kind of draw the exterior on the inside now. Then I can show how light rays exit from the boundary of the future of the, so this is the interior, this is the boundary of its future, and these light rays exit here because they run into each other and they're no longer on the boundary of the future. Okay. So this is just some theorem in classical GR that holds when the null energy condition holds. So now I've got a problem, right? So all of those light rays are going to leave the boundary of the future before lambda equals 2. So that tells me that my regular L in our setting, where there's negative expansion, is actually going to be a subset of the curly L. It's the opposite of the situation that I showed you here. Okay, so that means that the regular L is compact, right? Because it's a closed subset of a compact set. And that in turn means, although you have to sort of work a little bit harder to really show that rigorously, that means that the exterior of this surface T must also be compact. You can't have a non-compact half Cauchy slice evolve into a compact one. Okay, and now we have a contradiction because we assumed that this thing here was non-compact. So what has to happen is that in fact these geodesics cannot be extended as far as lambda equals 2, and so there's a singularity. At least one of them cannot be extended in this way.
Stupid question.
Yeah.
So Nat would tell you that each geodesic has a focal point, right? Each null geodesic has a focal point, but they all don't necessarily meet at the same focal point, right?
That's correct. Yeah. So what this theorem tells you, sorry, where's my theorem? There, actually, yeah, is at or before. So the null energy condition implies that there's a conjugate at or point at or before lambda equals 2. That doesn't mean that other bad things couldn't happen first, right? But in particular, it doesn't say anything about this conjugate point having to be 1 point for all these geodesics. So you just follow a bunch of, like you look at this geodesic as it's coming out of the surface, and if it has negative expansion -1 here, you know it can't last longer than Fm parameter 2. But typically, yeah, it'll exit sooner. Maybe it will run into a non-local intersection with a geodesic from far away. That'll also terminate. That also means it leaves the boundary of the future. It leaves this regular L. There's lots of ways it could leave regular L. This is just giving us, it's just making sure that it will do so no later than lambda equals 2. Yeah. Great. Any other questions? Okay, so the singularity theorem that Arvid and I proved, doing very little extra work, is for hyperentropic regions. So what we're doing is switching out the assumption that Penrose made that one side of T is non-compact, and it had to be the side towards which the light rays have negative expansion. We're switching that assumption out for a weaker, with a big asterisk, assumption that the exterior of T has a lot of entropy. By a lot of entropy, I mean that it has more entropy than the Bekenstein-Hawking entropy of T itself. Okay, and I'll say in a moment why this is, in some sense, a weaker assumption. Okay, but actually, we have to make another assumption, which is that the covariant entropy bound holds. So just going back to the picture that you already saw here, what we're going to be assuming is that the entropy in this exterior region, the one whose light rays we're investigating, is larger than this area. And we're also going to assume that the covariant entropy bound holds, which means that the entropy on this light sheet must be less than this area. And you can see how this is going to be a contradiction, because all the matter that sits here has to pass through that light sheet. So it's not going to be a huge shock that results in a contradiction. So how do we know this L is going to be a light sheet? Well, a light sheet is a null hypersurface with everywhere non-positive expansion. Okay. We know that coming out of T, we're going to assume, we're changing nothing else about Penrose's assumptions. So we're still going to assume that T is, has negative expansion in some direction. Okay. And if the light rays are initially have negative expansion, then the null energy condition guarantees that they can only get more negative. The expansion can only get more negative. And so L is a light sheet. Right? It's never going to have positive expansion. L is still defined as before, as the boundary of the future. And so we can apply the covariant entropy bound to L. So the proof is actually very simple. The previous proof has already established, well, actually, we spent quite a few pages in our paper really making this rigorous, but in the picture it's obvious that the domain of dependence of L is the same as the domain of dependence of the exterior. Right? That was the whole point of showing that this L is compact. That sort of means it closes off and it forms a good Cauchy surface for this region. And so that means the entropy on L is the same as the entropy on the exterior of T. And so now you have a contradiction between the assumption that the entropy here is bigger than A and the covariant entropy bound, which tells you that the entropy on L is less than A. Why is this a weaker assumption than Penrose's non-compactness assumption? Well, let's go back to our initial example here with this collapsing star that forms a black hole. And let's say we want to apply our theorem to this surface T here. Surface T has this negative expansion going out this way. We can certainly apply Penrose's theorem to it. That's what we did here. But it looks like we can't apply our theorem because the way I drew this, there is no matter out here on this exterior part of the Cauchy surface. And so the entropy will be 0, and it will certainly not be bigger than this area A. And so our theorem doesn't apply. So that makes it look like our theorem, at least in some situations, is weaker, right, than Penrose's or our assumption. Certainly, yeah, our assumption looks stronger. The theorem looks weaker in this example. However, because the exterior is non-compact, I've got this asymptotic region over here where I can add as much entropy as I like while changing the metric as little as I like. I can add what might be called soft photons, right? Just whatever this area is, let me, in Planck units, let me add twice as many photons out there. And let me make them, I can make each photon the wavelength as large as I like, right? There's plenty of room. And I can space them out as far as I like. And so I can add a lot of entropy while changing the metric as little as I like. So I won't change the singularity structure of the space-time. And so I can get to a situation where I can apply our theorem without changing the singularity structure. So then I'm good. Okay. So here, well, in all of these cases, so this is sort of the regime of the original covariant entropy bound. The entropy is defined in some thermodynamic sense. Like if I give you a box of gas, use your undergraduate textbook to compute its entropy, and don't sweat over things like quantum field theory divergences. When I ask about the entropy in this room, you kind of know how to calculate that, and you're not going to lose sleep over the fact that there's an area term that diverges in units of the cutoff. Or to put it differently, subtract those universal divergences off. Take a renormalized entropy. I'll get to a quantum improved version of this theorem which does better than that. But right now, just, use the entropy from the undergraduate textbook. Good. Any other questions about this? If not, I'll give a couple of examples just to illustrate that there's really stuff that it can do that Penrose's theorem couldn't do, so it's nice. Let's first go back to this example of the collapsing star. Here's your sort of, I don't know, not very accurate non-space-time drawing of this. The star collapses, and then it forms a singularity. This is what the Penrose diagram looks like. But what this diagram shows you nicely is that the surface area of the star goes to 0 when it collapses. That's not so obvious from the Penrose diagram, but the area is actually 0 up here, right? That means that I can apply our theorem to this interior region. I'm going to call it exterior of T because that's always what I'm going to call the direction in which light rays go that we're worried about. So here, at sufficiently late times, if the star had some large entropy to start with, that entropy can't go down, right? But the area is decreasing, so it's going to have more entropy than the area of the surface of the star. And our theorem says that these light rays have to terminate, because if they didn't, then all that entropy would pass through the light sheet and the covariant bound would be violated. This is nice because who knows, maybe this universe was secretly closed at very large distances. It'd be kind of weird, right, if in this situation, whether or not there's a singularity depends on what the universe is doing globally, very, very far away. So our theorem is not sensitive to that. It doesn't care if the universe is closed or not. The physics that determines that we have strong gravity that will lead to a singularity is kind of much more local than that. It's not totally local, but it doesn't depend on global properties.
Raphael, since I'm using my undergraduate entropy,
Yeah.
that's, there was a part of the proof that was talking of matching the entropy on your original slice to the entropy on the light sheet.
Yeah.
So was there an inequality there? Because my undergraduate entropy obeys the second law, right? It's not.
Yeah, well, that would only help, right? Because then, yeah.
But the question was whether, because Penrose's original thing is timesymmetric, and you apply it to initial singularities.
Yeah.
It's not going to work.
No, I mean, you do get to work with a fine-grained entropy, if you like. So there's two issues. One is whether the entropy sort of increases towards. You don't have to say that. So, but on the other hand, to make the theorem more likely to apply, you might as well first coarse-grain the entropy. In other words, work with a quantum state that doesn't change the metric, but has more entropy so that the theorem is more likely to apply, right? But then you don't have to say that that entropy still increases as you evolve forward in time. You can work with the fine-grained. The important thing here is that you don't worry about things like area terms and other divergences that occur in quantum field theory. Yeah, so here's another example. Let's consider the time-symmetric slice here, t equals 0, whatever you want to call it. And you can easily construct time-symmetric initial data which have a lot of entropy hidden behind the bifurcate horizon of the vacuum Schwarzschild solution. Okay, so this unfortunately the green is not rendering very well in this on this screen, but until about here, we just have the vacuum Schwarzschild solution. This is one of these cut and paste constructions similar to the Oppenheimer-Snyder solution. But here I've kept the vacuum Schwarzschild solution beyond the bifurcation surface. So there's a black hole, a white hole region. And then if I kept going, I would have another asymptotically flat region over here on the other side. But I won't keep going. I'm going to glue right here to most of a closed recollapsing dust-filled universe. Again, that's easy to do. You can match everything. And you can make this as big as you like. So you can put as much entropy there as you like. And here's a surface which is actually perfectly normal. In other words, it's a sphere that has the property that the light rays are contracting towards what you would ordinarily call the inside, the side that's not infinity. But our theorem applies both in the past and in the future direction because we've put so much entropy over here. This is a sphere maybe a little bit outside the black hole horizon. We can easily exceed that entropy. And so the theorem predicts both this past and this future singularity. Again, that's not something that Penrose's theorem would have been applicable to because this direction is compact. And then as a final example, it's nice to think about a universe which is just closed to start with. Let's say this Interspace, so that Penrose's theorem wouldn't have applied to start with. It's closed. We start with a vacuum de Sitter solution, let's say. So I didn't draw that here, but remember the space in sort of an embedding picture, vacuum de Sitter solution looks something like this. It's a 3-sphere whose scale factor goes like the cosh of time. So it shrinks and then later grows exponentially. So it grows very rapidly. So let's take one of these spheres, in the far future, a really huge, exponentially large 3-sphere, and let's sprinkle it with a little bit of radiation, some really low temperature thermal state, let's say. We can put that there, and we can keep the back reaction arbitrarily small by just making the temperature low. And if we're not happy yet, then we can just say, OK, let's go to a later time instead where we have even more space to do this. And what you can arrange, right, is what I'm going to be interested in is T being the equator, just for simplicity. Okay. So what I'm trying to arrange is for there to be more entropy in one hemisphere than this area. And that's actually easy to arrange while keeping the back reaction small, simply because the volume of this hemisphere grows like the scale factor cubed, and the area only grows like scale factor squared. So we can do this. More specifically, the entropy in the exterior of T is whatever radiation density I put there to the 3/4 power in a thermal state. One thing goes like T to the 4. This goes like T cubed, the entropy density, times the volume. And I'm dropping any factors of order 1. I'm going to make that bigger than the area of T, which goes like a squared. Just by taking a large enough, I can do this at arbitrarily low rho rad. Okay. What's nice about this is that, well, so clearly this light sheet here is contracting. That's another thing we need to make sure happens for the theorem to apply. It's contracting because it's coming out of the equator, so spatially the area is going to get smaller. And time-wise, well, we're going back in time, the universe is contracting that way, so this light sheet is definitely contracting. And so the theorem applies, and it tells us that there's a singularity going back. So I took vacuum de Sitter, I evolved forward to a late time, I added some incredibly small amount of energy density to it. And the theorem knows that when I run this backwards, there's going to be a singularity, which is true. So what happens is that this energy density, of course, gets exponentially magnified by the contraction going back. Eventually, the radiation or whatever I put there is going to dominate over the cosmological constant, and it's like a closed universe that has a Big Bang. But it's nice that the theorem knows this, because we could make this time arbitrarily large. So this is not some nearby singularity. This happens very, very far away.
Raphael, so you could get the same conclusion by solving the three Roberts-Walker equations, but this is for anisotropic for inhomogeneous as well as thermal slice?
Right. So then, exactly, the sort of added value here compared to explicit solutions where you know the singularity is there anyway is that when you perturb it, you know it's still going to be there.
Does it say that there are no geodesics that may pass the probe, or does the sum geodesic fits the singularity?
The theorem only guarantees that at least one of the geodesics in the congruence that generates the light sheet L is incomplete. Though, of course, I suspect that none of them will. Yeah. I suspect all of them in this example will be incomplete. Yeah. It's not hard to generate trivial examples where some geodesics don't have that property by having, for example, other components of T. But yeah. But yeah, the theorem is sparse in its conclusions, just like Penrose's. In particular, it tells you nothing much about the nature of the singularity, but there's some curvature and invariant diverges there. Yeah, same limitations in that respect as Penrose's. Any other questions before we move on to the quantum version? How am I doing with time?
11 minutes.
11. Very precise. OK. So, right. So there's a sort of upgraded version of the covariant entropy bound, which leads to, you might think, an upgraded theorem, but it's one that is so upgraded that we're losing some sleep over it. So let me first introduce the upgraded covariant entropy bound. It's kind of confusing, I think, a little bit confusing to call it the quantum covariant entropy bound, because, of course, entropy always comes from quantum mechanics. So the original entropy bound also talked about entropy that was ultimately quantum in nature. What this one does is it deals with quantities that are a little bit better defined in that you combine the entropy in a spatial region with the area and whatever other counter terms are necessary to obtain a quantity which is cutoff independent. So in quantum field theory, if you ask about the entropy in a spatial region, we really should be worrying about terms like area of the boundary of the region in units of the cutoff. Or then usually there are subleading divergences like log divergences and so on. Okay. I'm not going to mention those at all. I'll just keep the leading term here. But what we've learned is that you can get a nice quantity that seems to be more robust by combining the entropy with a counter term, also known as the Bekenstein-Hawking entropy, that assigns some entropy to the area of the boundary. And then there are subleading divergences that have subleading counter terms assigned to them. So we'll work with this so-called generalized entropy. That's the sum of these two things. This G Newton has a cutoff dependence in it, and so there's a chance that things will cancel, and apparently they do in examples that have been studied. And there's a version of the covariant entropy bound which can be stated as simply an inequality between two generalized entropies. Namely, here you've got some Cauchy slice. Again, it's split into two pieces by some surface T. So let's pick some side and call it the exterior. And let's suppose that the generalized entropy is decreasing away from T in this light-like direction. So by decreasing, what I mean is that a certain functional derivative called the quantum expansion is negative. What is this derivative? Well, you've got your surface, and you've got your generalized entropy sitting here on one side. And now you can ask what happens if I deform the surface locally along a light ray with some infinitesimal cross-section. And I ask, how does the generalized entropy change? Well, that rate of change is related to this. The rate of change, more precisely, per unit area across which you deform, that is the quantum expansion. It reduces back to the classical expansion in the limit where GH bar goes 0. So you can think of it as the classical expansion plus some quantum correction that comes from the rate of change of the von Neumann entropy on one side of T. Okay. So when this quantum expansion is negative, then we believe it is true that it can only get more negative, just like the classical expansion. That conjecture is called the quantum focusing conjecture, and it was made in this paper. Okay. I'm going to assume that this conjecture is true, although more precisely what I'm really going to assume is that the conclusions I'm going to draw here are true. Namely, so clearly if this holds, right, you expect that the generalized entropy on the exterior of this cross-section of the light sheet T prime is going to be less than the generalized entropy I started with up here, just by integrating this expansion. Okay, it's increasing, and it can only it's decreasing going this way, and the generalized entropy can then only start decreasing faster if this conjecture is true. So it'll be less here than there. Okay, that is the quantum covariant entropy bound, the statement that the generalized entropy here is less than there if this expansion is negative, if this quantum expansion is negative. And that's ultimately the only statement we're really going to need. That's the assumption that's being made. Any questions about that? I should say that you can unpack. So you can make that start looking like the original covariant entropy bound by unpacking the generalized entropy in terms of as a sum of area and von Neumann entropy, and then putting all the von Neumann entropies on one side and all the areas on the other. And then you get something back like what I told you earlier about the entropy on light sheets being bounded by their area. Why is it nice to have a quantum version or this improved version of the covariant entropy bound? Well, for example, and this is really just an example, here's something the original covariant entropy bound did for us. It included as a special case the statement of the generalized second law when black holes form or when matter is added to a black hole. Let's take the case where a black hole forms. So this star, it had some entropy, and it made a black hole and disappeared. Looks like the entropy was gone. The generalized second law tells us, as Bekenstein conjectured it, that the area of the black hole that forms as a result must at least compensate for that lost matter entropy, the area in Planck units. Okay. Well, if I apply the covariant entropy bound to this particular cut of the horizon, some late time cut of the horizon, first of all, Hawking's area theorem tells me that the expansion in this direction is going to be negative. The area of the black hole horizon decreases or stays constant towards the past. So this is a good light sheet. And this light sheet contains the star that made the black hole. So the covariant entropy bound tells me that the entropy of the star is less than this area. That's precisely what the generalized second law demanded for black hole formation. So in the special case where the initial surface lies on a black hole event horizon, the covariant entropy bound reduces to the generalized second law. That's really nice, but it stops working once I have an evaporating black hole. And so now I'm very unhappy. So in an evaporating black hole, the problem is that this is not a classical light sheet anymore. The area is actually getting smaller towards the future because of the evaporation. So I can't apply the classical covariant bound. In fact, it might actually be wrong, right? If the black hole is almost completely evaporated, this area might be smaller than the initial entropy of the star that got lost. However, what still does apply is the fact that the quantum expansion is decreasing in this direction. That's because when a black hole evaporates, while the area goes down, it produces a bunch of entropy in the Hawking radiation outside, and that turns out to be more important than the area loss. So the generalized entropy is decreasing towards the past, increasing towards the future on these slices, okay, and also on the inside. So as a result, the quantum version of the covariant bound still implies the generalized second law for black hole formation, black hole evolution, and so on.
So you're counting Hawking partner. You have to count Hawking partner.
So so you get to choose which side you want to apply it to. If you choose this side, then the Hawking radiation provides the increasing entropy. If you choose that side, then the inside partners of the Hawking radiation provide. Yeah. You have to, there's a lot of entropy in here. The same entropy that makes something in here be an island at late times.
So then it's only one entropy. It's clear in this context.
Yeah.
Not necessarily just post-graining or real material.
Yeah, but again, I wanted it to be a von Neumann entropy either way. It's just that previously I didn't worry about area terms and other divergences that are associated with quantum field theory.
Yeah.
So it's more like a quantum mechanics to quantum field theory transition in how we treat the entropy. And indeed, the problem here is that the null energy condition, of course, isn't satisfied in the real world. It's not satisfied in any relativistic quantum field theory for appropriate states. And it is certainly not satisfied near the horizon of this evaporating black hole, which is why it's evaporating. OK. So what are we going to do with this quantum version of the bound? Well, it's convenient, and we can always do this, to have another system that doesn't participate in the in the evolution that takes us from one slice to another, and which just acts as a reference system that might purify some matter in the region of interest B. Okay. If we don't have such a region in the space-time, then we can always add it as an auxiliary system exterior to the space-time. Okay. So we'll consider two systems, B and R, or two regions, B and R. And we will take our initial surface to be their boundaries, but then we're only going to be interested in varying one of these boundaries, the one of B. Free to make those choices. What's going to be important to us is that the quantum expansion of B and R together is not positive, starting off in this direction. Okay. Now, the conflict, okay, that we're going to run into is the following one. Okay. If this light sheet here is complete, in the sense that it's compact, everything closes off nicely, then the quantum covariant entropy bound means that the generalized entropy of B and R, which is what's on one side of the surface to start with, is greater than, well, anything else I get by sliding this boundary down this light sheet, including sliding it all the way to the empty set, then I just get the generalized entropy of R. So the quantum covariant bound tells me that this generalized entropy of BR is bigger than the generalized entropy of R alone. So then I can clearly get a contradiction if I can see that to start with, oh, I'm sorry, this should be an R. If I just check from the beginning that Sgen of BR is in fact less than Sgen of R, then there's a conflict. Well, the conflict is that L can't be complete. Okay, I have to have a singularity that chops it off. All right. Now, I spoke as though the entire proof of the classical case just carries over here. And that's almost true. But there's one aspect of the proof which does not carry over. Let me go back to this proof. This is really going back all the way to Penrose's proof. Here. In the classical case, we had some negative expansion, let's say -1. Then the null energy condition implies that there's a conjugate point before lambda equals 2 for Fm parameter 2. Here, what we know is that we have a negative quantum expansion. Okay. The quantum focusing conjecture, which is what replaces the null energy condition in the proof, tells me that this expansion can only get more negative, but it does not tell me when it has to go to -infinity, which is when this conjugate point happens. It doesn't tell me that that has to happen before this or that affine parameter. That turns out not to be a problem. Okay? There's a different argument that you can make, which tells you that the light rays cannot stay on the boundary of the future or of the past, whichever way you're going, for infinite affine parameter. And that's actually all that you need. It was not important in this proof that I knew that lambda equals 2 is the magic place where they have to have left the boundary of the future. It was just important that they do so after some finite affine parameter. And we can use an argument of Wall that he used to generalize. So Aaron Wall in 2011 generalized Penrose's theorem in a different way from what we did. He didn't eliminate the non-compactness assumption, but he did eliminate the null energy condition and replaced it by assuming the generalized second law of thermodynamics. What you can show is that if a light ray that started with negative quantum expansion stayed on the boundary of the future of of the region forever, it would define a causal horizon to which the generalized second law can be applied. And you can then derive a contradiction between the sign of the expansion that you started with and the sign of the expansion implied by the generalized second law. And so you can conclude that it can't be true that the light ray stays on L forever. That argument still applies to us. And so, we can use it to show that L, if all the light rays were complete, L would be compact, and we would have this kind of contradiction. So you can still conclude that there's a singularity. And now let me end with a puzzle. How many minutes do I have? Minus, oh boy. Great. So the puzzle is this. So here I formed a black hole and it's evaporating. And unfortunately, the R is covered up, but it's over here. It's this part of the Hawking radiation that's already arrived at distant regions. And the quantum expansion going backwards along the horizon is negative. So what I need for the theorem to apply, right, is that the generalized entropy of B and R together is less than the generalized entropy of R. In this case, this is just the entropy of R. There's no area term since R is entirely at infinity. And that'll be true after the page time. Why? Well, the generalized entropy of B and R together, maybe it's easier to see by going to the complement region. It's the same as the generalized entropy of a slice that connects from TB up to this cut at infinity. And that's just this area. There's almost no radiation here. Another way of saying that is, well, it's the area plus the entropy of B and R, but B and R together have no entropy because these are the inside Hawking partners R and B that purify the Hawking radiation in R. So the entropy up here is just the area. That's the entropy of B and R. But the entropy of R is the entropy of the Hawking radiation, which is bigger than the area of the black hole after the page time, by definition of the page time. Okay. So the theorem's assumptions are all satisfied, but clearly there's no singularity down here. I mean, I made this but from regular initial conditions. I collapsed a star, formed a black hole, let it evaporate. So the question is what gives, right? So one logical possibility is, of course, that one of our assumptions is wrong, presumably the quantum covariant entropy bound or something. But it's kind of weird. I mean, this is just a natural quantum generalization of the classical theorem, which was doing just fine. What we currently think is probably the resolution to this puzzle is that when we follow these slices back, there's actually more than one thing that goes wrong. For example, formally, the generalized entropy on these slices goes negative before we even go down here. That doesn't make any sense. Generalized entropy is supposed to represent some actual von Neumann entropy in a quantum gravity theory, and it has no business becoming negative. Well, in fact, something else happens as we look at slices that go further and further back, starting at R. And we're fixing R. Remember, that was sort of our reference system, which we're not moving. It turns out that these slices look like they're becoming what's called not nice slices in the technical sense of the word. The technical sense of a nice slice is one which has small intrinsic and extrinsic curvature and no energy densities that are Planckian or something like that. So they have to have, everything has to be sub-Planckian so that you have a good effective field theory description of them. You can't actually go back much further than a scrambling time or so, radius times log entropy, which is a much smaller time scale than the page time, without being in a situation where you cannot find any nice slices to foliate the geometry. So our current best guess is that what this theorem is teaching us is that we should think of the semi-classical regime as failing when there are no nice slices. That is like running into singularity. You can't evolve further. And so that's the singularity that's predicted by this. Okay? But it means that the sense in which there's a singularity here depends, in some sense it becomes observer dependent, or it becomes data dependent. It has to do with the fact that we're not allowing this radiation to participate in the evolution as we're going backwards. It becomes more obvious if I just take this radiation and move it out of the space-time. That doesn't change the applicability of the theorem, but then it becomes immediately obvious that you get a singularity here from the fact that the vacuum is not restored when you evolve backwards. Anyway, I'll stop there and take some questions. Thanks. Say that again, sorry.
If you assume the Arons-Wald singularity theorems using the GSL, you get kind of the similar singularities?
No, I wouldn't get this one because Aaron would require this region to be non-compact for his theorem to apply. So I don't think I can get any bizarre examples like that from Aaron's theorem.